everyone, I'm at home now, so I'm going to be trying out some different formats for videos and see what works. To start, we'll try this whiteboard that I brought home from my office. So I want to pick up where I left off in class. I had just finished ideal gas processes, and now I'll start heat engines. So a heat engine is a closed cycle system, which means that it returns periodically to its initial condition. So it's a repetitive process, and it works by extracting energy from a hot reservoir, using that energy to do useful work, and then expelling the leftover energy to a cold reservoir. So I've just outlined these steps here, the process of a heat engine. So first step, energy is transferred from a hot reservoir. The amount of energy that's transferred will be called QH, and then part of the energy is used to do useful work. So to indicate that this is the work done by the engine, it's WENG for engine, and then the remaining energy is transferred to a cold reservoir. And we can say a little bit more about those terms based on what we know from the first law of thermodynamics. All right, so if you recall, the first law of thermodynamics is that delta E thermal for a system, the change in thermal energy, equals the energy transferred through heat plus the work done on the system, on the gas in this case. And so this is the first law of thermodynamics. And I mentioned before that for a cyclic process, that returns to its initial state, because the temperature would have to be the same in that initial state, the overall change in thermal energy is zero. So this would also be true for closed cycle that returns to that state periodically. So since delta E thermal is zero, we have to have the work done equals negative Q. Now this is the work done on the gas. In this case, we're interested in the work done by the gas that goes into doing a useful process. So we want the work done equals negative of the work done on the gas is negative of the work done by the gas. So we get the work done by the gas equals Q. And this Q is the net heat transfer. Heat transfer is the difference in the energy in compared to the energy out. So we can calculate Q overall by taking the difference between QH, the energy transferred in from the hot reservoir, and QC, the energy transferred out towards the cold reservoir. And all of these values, the work done by the engine, the heat transfer from hot and to the cold, they're all energy transfer in joules. So far all of our units are in joules. Just to note as well that this work done by the engine is the negative work done by the gas, which I've said, but before we found that work done by the gas by taking the negative of the integral, the P versus V graph, so the area enclosed by the P versus V diagram. So it still can be calculated that way, it's just now that it's positive, so the work done by the gas is the area enclosed by the PV diagram. So some examples of heat engines are car engines, steam generators, and in the case of a car engine, for example, the hot reservoir could be fuel, so burning fuel, taking in that energy, and then returning it to the air outside, which is the cold reservoir. So this word reservoir really means that it's part of the environment that it's so large that if there's some energy transferred to or from that reservoir, it doesn't make any difference overall. And that applies to both reservoirs here. Okay, so one more thing I want to talk about is the thermal efficiency. So as we know in real life, any of these processes are never 100% efficient. So they take in some energy and they release energy, and in this case, that is what's happening with the cold reservoir. So we can calculate the thermal efficiency of a heat engine by taking the energy output, which is this work done by the engine, over the energy in, which is QH. So I have the net work per cycle over the energy input. And that gives us the thermal efficiency here. So we can also write it, instead if we plug in for Wn, we have QH minus QC over QH. And then we can simplify, so dividing by QH will give a 1 here, 1 minus QC over QH. Just have absolute values so that this process is general. We're taking just the energy in joules for each of those processes. And so no real life process's energy is 100% efficient. As I said, there's always some energy that's released to another reservoir. Not all of that energy that comes in can go into performing that useful task. Okay, so let's get started with the first example. An engine transfers 2 times 10 to the 3 joules of energy from a hot reservoir and exhausts 1 times 10 to the 3 joules per cycle. A, find its efficiency, and B, how much work does it do per cycle? Okay, so I've listed the given information here. We're given QH and then QC, the exhaust. And first, to find the thermal efficiency, we can use this version here. This symbol is eta, by the way, for efficiency. 1 minus QC over QH, and we can just plug that in, so that's 1 minus, this will be 1,000 joules over 2,000 joules, so 1 minus a half gives us 0.5. You'll see efficiency listed like a decimal like this, so 0.5, something less than 1, or as well as a percent. So we could also multiply this by 100, and say that it's 50% efficient. Okay, and then when we calculate the work done by the engine, we want the difference between QH and QC. So this will be 2,000 minus 1,000, which is 1,000 joules. And that's the work done by the gas per cycle. On to example 16, which says, what is the thermal efficiency of the heat engine? And it has a diagram like this of the heat engine. So it's going from 20,000 pascals to 40,000, and then we have 0.1 to 0.2 meters cubed for the volume on the bottom axis here. And this is a closed cycle process, and we're also given that QH is 4,000 joules. So as I was saying, the work done by the engine is the area enclosed by that PV diagram. So we can calculate that using simple area formulas if possible, like in this case, so 1/2 base times height. So that will be 1/2, this is only 0.1 for the width here, 0.1 meters cubed, times the height, which is 20,000 pascals. And we end up with 1,000 joules there. And then to calculate the thermal efficiency using this definition, the work done by the engine over QH, since we have that work done, is 1,000 over 4,000. So 0.25 for the efficiency of that engine. So a quarter or 0.25 or 25%. And this is realistic, so real heat engines usually have an efficiency between 10 to 50%, so it is fairly low. All right, so I want to go through some steps for solving heat engine problems. Okay, so steps for solving. And the first step, I would say, to identify each process and draw a PV diagram. So let's start with draw a PV diagram. It really helps to have a visual of the process. Then we'll use the ideal gas law in order to calculate any missing information for each state. You can make a chart here if it helps and find the pressure, the volume, and the temperature at each state. Okay, and then we're going to determine the heat transfer, Q, the work done in each case, and also the change in thermal energy for each state. Let's say for each transition. And we went over all of the rules for finding those in class. And you can refer to my lecture notes for that, and we'll go through some examples in a second. And then we'll find the net work done. So let's just say that we'll just find the work there first. And then step 5, we'll say find the net work done by the engine and the total heat transferred in each case. So QH, the total heat coming in, and then QC, the total heat transferred out of the system. And then lastly, with those values, we can find the efficiency. So these are longer problems, but can be very systematic to solve. All right, let's move on to example 17. So we have a heat engine uses a gas for which CV equals 20.8 joules per mole Kelvin and CP equals 29.1 joules per mole Kelvin and undergoes the cycle shown in the PV diagram. How much work does the engine do per cycle and what is its efficiency? All right, so I've drawn out the cycle here so you can see it. It looks like this. We have the pressure going from 1 to 3 atm and then the volume from 3 to 1 meters cubed. And we're also given this isotherm line here to say that anything on that line is 300 Kelvin. So we know at 0.4, that's 300 Kelvin. Okay, so let's set up a table. So this might be helpful to make a table like this where we have all of the states along the top, 1, 2, 3, 4, and then the pressure, the volume, and the temperature. We've done one like this before as well. And then fill in what we have. So we have all of the pressures. Make sure to convert them to pascals instead of atm. So 1 atm is this, 101,300 pascals. So then we're given that. This is 3 atm. And we're given all the volumes if we look at the chart. So these 1 and 4 are at 1 meter cubed, and 2 and 3 are at 3 meters cubed. So in order to find the temperature, we can do this one of two ways. I'll show you one way that I have on the board here first. So first we are given 300 Kelvin at state 4, so not here. Let's move that to state 4, 300 Kelvin, where our isotherm is. And then we can calculate the number of moles, which we'll need later anyway, so let's do that now. So using any of the states where we have all three information, it's only state 4 right now, so we'll use state 4 using the ideal gas law. So PV equals nRT, and then N is PV over RT, and we get 40.6 moles if I plug that in. Then you can apply the ideal gas law at every state to find the temperature. So I did state 3 right here, P3V3 over NR, just rearranging the ideal gas law, and plugging in the numbers from state 3 will give me 900 Kelvin. And you can keep doing that if you'd like for each state. It's simple enough. Or I'll just erase to show you the other way. Which would be to use the ideal gas law for transitions. So since we know N and R are constant for each state, we have PV over T. For example, if we chose state 1 to state 2, it has to remain constant. So we would have P1 V1 over T1 equals P2 V2 over T2. And I can show an example. Maybe let's do, to find state 1. The the process is isochoric, meaning that the volume is constant if you look back at the last diagram. So we'll have P1 over T1 equals P4 over T4. And then rearranging this, I get T1 equals P1 over P4 times T4. Just cross multiplying and dividing. And then if we plug that in, that would give us P1 over P4. So 1 over 4, which is going to be 3 times T4. So that will give us, again, 900 Kelvin. Okay, so 900 for state 1. And then if you like, you can also apply the same relationship to find state 2. You could apply to any of the same transitions or use this law. And I'll just put the answer. You'll find 2700 Kelvin. Okay, so we have all that information here. Feel free to pause and then compare your result. And I'll just erase so that we can get on to finding the work and the heat transfer in each step. Okay, so I've made the chart so that now we can have a look and calculate the work done by the engine, Q, the heat transfer, and then delta E thermal for each step. So each transitions, we have 1 to 2, 2 to 3, 3 to 4, and 4 to 1. And I may have to pause in order to do some erasing, but we'll work with that. Okay, so you can start anywhere. Let's start with 1 to 2. This transition is isobaric because it remains at the same pressure. And for isobaric, we have to calculate both items. So we have work done by the engine is P delta V. So that's going to be the constant pressure of 3 atm, which was 303,900 pascals, times this change in volume, which is from 3 to 1, so 2 meters cubed. 3 minus 1 meters cubed there. And that gives me 607,800 joules. And we can put that in 1 to 2, 607,800. So all of these numbers will be in joules in the chart. And then Q, we have the heat transfer using the specific heat at constant pressure. So Q equals NCP delta T. So that's going to be 40.6 mole. CP, which was given to us for the gas, it was, let's see, 20.8. Oh, actually 29.1 is CP, 29.1 joules per mole Kelvin. And then we have delta T from 2 to 3, which you can flip back to the other chart to get those numbers. So that's 2700 minus 900 Kelvin. And then that gives me, let's see, 21. Just copying that and then I'll say it. So what is that? We have 2,126,628, and we can subtract. So I've written in here for each of these steps, once you have these values, you can take Q minus the work done by the engine and put that number right there. So this time it's 1518828. You can round, it's not a big deal, but I'll just leave all the digits for now. Okay, so that was 1 to 2. I'll just pause and erase, and then we can do, okay, so we can do 2 to 3. So I've switched that up here. 2 to 3 is isochoric because that's at a constant volume. And as you can see, the area under that vertical line, of course, is 0, and delta V is 0, so we end up with the work done by the engine at 0, which means that Q is equal to the change in thermal energy, and the heat transfer at constant volume is NCV delta T. So that will be 40.6 mole. This one's 20.8 joules per mole Kelvin. And if you check the temperatures, this was 900 at state 3 minus 2700 at state 2. And that gives me a negative number of negative 1, 5. I think it's the same as the previous number. I'll just double check that. So that's going to be 40.6 times 20.8 times 900 minus 2700. Yeah, so with rounding, it's a little bit different. I get 152, 0064. So we'll put that here. In both of these columns, negative 152, 0064 joules. Yeah, okay, they're all in joules, so I can erase that. Okay, so we've got those two numbers and 0 for 2 to 3. So let's do 3 to 4. Okay, now I've got 3 to 4 up here, so if you have a look, I filled this one in already. It's very similar to what we did already for 1 to 2, since it's also isobaric. We can use work is P delta V, and for this transition, it's 1 atm, 101,300 pascals, and then I have the volume 1 minus 3 meters cubed to give me negative 202,600 joules, and I've written that in 3 to 4 as well. And then Q is NCP delta T, so our moles, 29.1 joules per mole Kelvin, and then 300 minus 900 if you flip back to the temperature chart to give me negative 708,876. And then if we do Q minus the work done, we get negative 506,276. So one left, let's do 4 to 1. All right, last one, 4 to 1, isochoric again, so that means that the work done is 0 since there's no change in volume there. And then we have Q equals NCV delta T. I've just plugged in the numbers 40.6 mole times 20.8 joules per mole Kelvin, and then temperature 900 minus 300. And for that we get 506,688, and then I can plug that in here, and we have the same delta E thermal equals Q. Note that for any of these, we could have used this expression to find delta E thermal. So it's not always equal to Q, depending on the process, but I'll just erase this for a second. We always have delta E thermal equals NCV delta T. So this is another way to find this last step. It's a little bit easier to subtract if we've already done that work, but you could check that you get something similar if you use this value. It should be exactly the same, but we've done some rounding in the previous steps. And that's always true even if that's not the value for Q in each case, of course. All right, so now I want to erase so I can calculate the total values. All right, so we're ready to finish this up. So let's look at the total values. The work done by the engine, which we were asked for, is going to be the total, the net work done from this top row. So subtracting or adding those two values, which ends up in a subtraction, we get 405,200 joules. Okay, and then QH, we want to look at the heat coming in. That's the energy coming in from a hot reservoir, so it's the positive Q values here. So we have this number, and this one from 4 to 1, they're positive, so we can add them to get the number here. Now we don't need QC because that's enough to calculate the efficiency, but if you wanted QC, you could add up these two negative numbers to get the heat transferred out of the system. And if you want, as a check, you can check that the work engine net is approximately QH minus QC, subtracting those numbers, or if you added all of this up, you'll find basically add across this row that we get the same value as for the work done by the engine. Okay, so now our efficiency, the work done by the engine over QH, divide, and we get about 15% efficient. One more thing to notice for this cycle is that if you add up all of the total thermal energy transfers in each transition, you'll get about 0. So these two are almost equal to give us 0, and these two are 0 as well. It's exactly 0, but there was rounding. Even if we didn't round, keeping all these digits, as many as we can, there's rounding in the constants CP and CV. So if we're getting something that's very close to 0, that does verify that law for heat engines, since they're closed cycle, that we should have delta E thermal for the entire cycle. Okay, so last thing, I just want to talk about some realistic models for heat engines. And the Brayton cycle is a more realistic model of a heat engine, and this would power turbine engines, so maybe to run an airplane or for electric power generation. Okay, so what would happen is it looks something like this with 2 isobaric processes and 2 adiabats. So starting at 1, this would be an adiabatic compression, so the gas is compressed in a compression chamber. And then it will go through a process where it's moved to a combustion chamber, and then it takes in energy from fuel. So the fuel is burned and it takes in energy. And then here in this adiabatic expansion, the gas then will use that energy and spin a turbine. And then lastly, 4 to 1, it would move to something called a heat exchanger and transfer energy to a cooling fluid. So this is important because in the next section we'll come back to this for refrigerators. The reverse of this is the basis of a refrigerator. But there are other engine cycles. You can look up many. A common one is Otto cycle for gasoline internal combustion engines, or a diesel cycle for a diesel engine. So, but that's all for this section on heat engines, and we'll pick this up again soon with refrigerators.